I'd like to go ahead and get started and welcome everyone to the last Diatom Web Academy of 2022. We've had a full year of sessions, and David Burge will speak to us today. But before I pass it off to Mark, I just want to let everyone know that already our schedule for 2023 is in place. Bart Vandeveer will be speaking on January 17th. So we have a short break and then we'll pick up back up again. And I just put the link in the chat, and we've got a nearly full schedule for the spring. So it's great that we've had such a wonderful response from all of you, and that a lot of people want to speak in this series. So just want to thank everyone, because this has been very inspiring to me to be involved in. So I will turn it over to Mark to introduce today's talk.
All right, thanks, Sarah. Before we introduce David, I wanted to say one more announcement here. I just put a link in the chat feature, and if you have any connection at all to Lakeside Laboratory, where we teach the diatom class every summer in Iowa, or maybe you attended a NADS meeting there over one of the 3 NADS meetings that's been held there. We are going to be celebrating the 60th anniversary of the diatom class in the coming years, and we're looking for some ideas about how we might celebrate that and what people's sort of availability might be to participate in something like that. But feel free to open up that Google Doc and submit this short survey to the Friends of Lakeside Lab. They'd be happy to hear from you, and we'll be working to put together some fun activities around this 60th anniversary. All right, without further ado, let me introduce David Burge. David's a wonderful diatomist who's been working both at the Science Museum of Minnesota and at University of Minnesota Duluth, where he hangs his hat at the Natural Resources Research Institute, working on lots of Great Lakes problems. David's coming to us from Floodwood, Minnesota, and the Christmas Tree Farm today, and is going to be presenting on diversity and identification of Stephanodiscus. Thanks, David.
All right, thanks, Mark. And I guess since I'm thanking you for that introduction, I also want to thank you personally for all the many conversations and the creative ways you have found for me to look at diatoms over the past 10 years and have discussions and be able to work on Stephanodiscus. Yeah, I guess I'll jump right into it. Are we advancing? There we go. All right. So I should probably change the title from Diversity and Identification of Stephanodiscus in Lakes of Central North America to David's Tips, Tricks, and Frustrations in working with those tiny spiny diatoms. My goals for this talk are mostly, I'd like to just share with you some of my, I guess, knowledge and experiences I've gained in working with Stephanodiscus. Or as I will probably affectionately refer to them as Stephs throughout the talk. My experiences and these observations were gained working on biological monitoring projects for the National Park Service in partnership with tribes and the Minnesota Pollution Control Agency, on EPA Great Lakes surveys. The samples and observations come from lake surface sediments, sediment cores, visits to various herbariums, in Philadelphia and the Reimer Herbarium at the Iowa Lakeside Lab. So there's another plug for the 60th anniversary is the use of the herbarium there. And then, of course, more recently, with my position at the Natural Resources Research Institute, where I've been working as a phytoplankton scientist on the EPA's Great Lakes Monitoring Project, and those samples come from plankton toes. So a bit of a spoiler, and for the sake of narrowing down your interest, and maybe we'll see the participants run out of the room right now, but I'll mostly be focused on the smaller steps today. And by defining the smaller steps, I would say where the maximum sizes of the diatoms are below 30 or even 20 microns. I realized in putting this together that I'm actually naive to what I'll allude to later is what the Stephanodiscus niagara complex. There's probably about 5 really big steps that have some subtle differences that I need to go back and do my homework on and learn. All right. So just a brief introduction to Stephanodiscus. It's a centric diatom genus. That is, the valve face has radial symmetry. The stria and Stephanodiscus are grouped into structures called fascicles, often occurring uniseriate near the central area or the center of the valve, and then radiating out and becoming biseriate, triseriate, and there's even some that have up to 6 areolae at the margins. And when I'm talking about a fascicle, just to illustrate it here, I hope I can do this. So here's a fascicle coming off the bottom of this Stephanodiscus Triporis. This is from Kiss et al. 2023. And in the center of the valve, the stria are organized into uniseriate rows, and then near the margins, they're becoming biseriate. In between the fascicles are just an area where that we call the interfascicle. Often in most Stephanodiscus, the interfascicles terminate at the face mantle junction with a spine. The number of spines and the occurrence of spines, whether they're on every fascicle or every other fascicle, can be a useful diagnostic feature. Sometimes it's just on every fascicle, and it doesn't differentiate between certain species, but we'll get more into that. Often below these spines, and I guess here we're transitioning to where a lot of work in Stephanodiscus diversity was really aided by the scanning electron microscope. In particular, there are 2 ultrastructure features that really revealed a lot of diversity within Stephanodiscus. You know, the fascicle and the areolae density in the fascicle is often something we can see in the light microscope. There's a couple of taxa that are difficult to resolve, but the phytoplankton and the remoportula of the Stephanodiscus, you know, sometimes can be observed, but most of the time are not observed in light microscopy. And this is where scanning electron microscopy really hurdled Stephanodiscus diversity. And so the phytoplankton can occur along the margins below spines. Sometimes they occur below every single spine, and sometimes they occur in rare cases right next to a spine. And the phytoplankton are just a very simple opening externally to the valve face, and then internally there are various structures around the internal opening of the phytoplankton that can be diagnostic. There can be little wings, there can be a vestibule. I guess the vestibule is actually characteristic to Stephanodiscus Triporis here. And then the other feature is the labiate process, or the remoportula, which opens internally with the shape of lips. But then again, both these features externally on the diatom are generally simple. The location of valve face phytoplankton and multiple remoportula can be very diagnostic. And I think these are very important features, but I'm not going to focus too heavily on them today. I just want you all to be aware that this is where some of the Stephanodiscus diversity comes from. And I'll mention this especially when we get into what I'll refer to as the Medius alpinus complex and the other 5 species that fall in with these cohorts and are diagnosed by these ultrastructure features, which are not resolvable very well in the microscope. So just be aware that there may be some of these taxa that seem almost identical, but I'm mostly trying to present today to talk to you about how you might encounter them as an analyst or a researcher who's just working with a light microscope, and that's predominantly how I have spent my career. Okay, let's see. Did I leave anything out? No. I will take a moment here to point out, if you're further interested in Stephanodiscus, authors like Eugene Stormer, Ed Theriault, Hannelore Hawkinson, Hockley and Tanaka have all worked extensively on Stephanodiscus, and there you're going to find a wealth of scanning electron micrographs that will help you navigate. And if you're looking for any literature on Stephanodiscus or some papers that might be hard to get a hold of, please feel free to reach out to me because I have gigs of them. Okay, moving on. Stephanodiscus in general occupy across all the species occupy relatively similar niches. They're often found occasionally in oligotrophic waters, but I'll make an argument for that in just a second. But more commonly in mesotrophic and eutrophic waters. Stephanodiscus are heavily silicified diatoms that sink very easily. And so they only really inhabit the plankton, the epilimnion of a lake if there's a lot of mixing, which can occur in shallow lakes from wind, or in larger, deeper lakes from spring and fall turnover when the waters mix. So the Stephanodiscus are often associated with these moving waters within a lake. They can also occur in the phytoplankton of some larger rivers, but they're often associated with moving waters. And in these moving waters, there's usually a higher abundance of phosphorus and silica. The cyclotelloids, Landavias, etc., they seem to have a bit better buoyancy control and will persist in the epilimnion, for instance, of waters longer than the stephs do. Now that saying, Stephanodiscus have evolved strategies or inherited strategies to help maintain their buoyancy. Out of those marginal photoportula that I described earlier, they can secrete chitinous fibers that essentially help increase their drag and remain suspended for light and nutrient availability in the top waters a little bit longer. Okay, so let's start with Stephanodiscus niagari and the complex, I'll say. Stephanodiscus niagari is the type of Stephanodiscus. It was described by Ehrenberg, and a lot of the characteristics that I'll describe here are translated across the genus. The valves are centric, and they're often concentrically undulate. That is, they kind of form to a cone or to a depression. Stephanodiscus niagari and its similar taxa are the larger stephs. They are 20 to 70 microns long. In niagari, the fascicles are often occurring in 7 to 9 per 10 microns. One thing I would like to point out as we move forward in working in centric diatoms and Stephanodiscus, using some of the literature and some of my old notes and some of my own observations, you have to be very careful in how you report fascicle density and centric diatoms. There's a method of taking a chord count, which you essentially put a 10 micron bar near the margin and count how many fascicles occur. Or you can do the circumferential density, which is where you divide the total number of fascicles by the circumference of the diatom. I have tended to gravitate more towards circumferential density, just because the subjectivity of placing a straight 10 micron bar at the edge of a circle, I guess leaves too much error for my consciousness. But just keep in mind when you're comparing Stephanodiscus and the literature on diatoms of North America, that the density can be measured in different ways. In my efforts of putting together DONA pages, I have tried to make it clear when I measured the circumferential density. All right, so sorry, that was a little side tangent and digression. So some other large Stephanodiscus that fall into what I am loosely just made up for this presentation calling the Stephanodiscus niagari complex are Stephanodiscus yellowstonensis, superiorensis, neoastria, heterostylus, and rotula. And the diagnostic features within these big stephs are the number and occurrence of spines and areolae and the marginal fascicles, and features of the ultrastructure like the phytoplankton. And for example, Stephanodiscus rotula has a smaller mantle height, a greater number of central processes, central phytoplankton, and generally a higher number of spines compared to Stephanodiscus niagari. And again, I didn't put together a comprehensive diagnosis between all of the large steps. I've realized I'm putting this talk together. That's a place where I need to do my homework. And
Sorry,
so here,
David,
moving forward, we're
this
going to
is
graduate into the smaller steps where that I've made a lot of observations on, and what I hope to convey some more clarity about. So working our way down, we have Stephanodiscus Transylvanicus. Transylvanicus is a larger, maybe a moderate size Stephanodiscus, occurring in 10 to 40 microns with 5 to 7 fascicles per 10 microns and based on circumferential density. I've never observed a bloom of Stephanodiscus Transylvanicus. I've often, I guess just recently observed it in my work at the NRI, where I've found it occurring in very low abundance in Lake Superior and Lake Huron in the phytoplankton toes. So it's not a very common diatom, but one of the very distinct features that distinguishes it for me is how broad the interfascicles are. As you'll note, the interfascicles are very, very apparent, and they are almost linear lanceolate in shape. But relative to other Stephanodiscus, this is just a very enlarged, distinct feature. Taxa that this could potentially be confused with, given its size, one might work on incorporating it into niagari or Stephanodiscus alpinus, but again, I think careful attention to the shape and size of the interfascicle really gives this diatom away. So moving along to another moderately sized common diatom is Stephanodiscus alpinus. And I'll spend a little bit of time differentiating alpinus and medius, which are two very similar taxa. Stephanodiscus alpinus occurs 12 to 30 microns in diameter. The fascicles occur in 12 to 14 and 10 microns. And the key characteristic of Stephanodiscus alpinus for light microscopy and diagnosis is that the fascicles end biseriate. So they're uniseriate near the central area, and as they move towards the valve margin, the face mantle junction, the fascicles end biseriate. And this is very important and maybe a reason to examine more than one specimen if you're able to examine the whole population to check for this this biseriate nature, is because Stephanodiscus, oh, now we're having trouble advancing, hold on. There we go. Stephanodiscus medius is a very similar sized diatom, slightly lower fascicle density, 6 to 10 versus the 12 to 14 of alpinus. Overlapping in size range, Stephanodiscus medius is reported to be a little bit smaller at 7 microns, but again, the very important diagnostic feature is that the fascicles end in 3 areolae at the margin, or they're triseriate. So this seems to be the most diagnostic feature separating Stephanodiscus medius from Stephanodiscus alpinus. Both the diatoms have spines often occurring on every single fascicle, although the spines are often broken through the processing of making slides. But the really key feature, and if you can look, I should have blown this up a little bit bigger, but that the fascicles here are ending triseriate. And we'll go back to alpinus here. This is the image from Lauren Balls's Diatoms in North America page. You can see here that the fascicles, I hope you can see here, sorry, that the fascicles are ending biseriate. Otherwise, I've seen Stephanodiscus Medius and Alpinus occurring in very similar habitats of medium-sized mesotrophic lakes. Maybe Alpinus is often occurring in slightly cleaner, lower total phosphorus lakes, but in general, they're both taxa that if you encounter either of them that look similar, they well warrant the time to look at the number of stria, the number of areolae, and the fascicle at the margin. Now, the triseriate nature of Medius, I guess, makes it a burden for this diatom, whereas Alpinus is easily distinguishable. There are at least 4 other taxa that are very similar to Stephanodiscus Medius. One is Stephanodiscus Kutzingii. The difference between Kutzingii and Medius, and this is only really detectable in scanning electron microscopy, is that Kutzingii has a valve face phytoplankton. Very similarly, with all these taxa, the differences from Medius are apparent in the scanning electron microscope, but not readily apparent in light microscopy. Stephanodiscus Organensis is another North American taxon, and it has a remiportula embedded with one of the spines. You might see in light microscopy a slight thickening of or maybe a better way to think about it is a greater occlusion at the end of one of the fascicles next to the spine because of the remiportula located next to it. However, it's not easily discernible in light microscopy. Again, this scanning electron feature. Another very similar taxon, and these are all very similar to Medius in their diameter and their fascicle density, and also the nature of the fascicles ending in triseriate. But they can be biseriate and they can be quadriseriate, but often a lot of these populations have a mixture of the number of areolae at the margins. Again, getting back to maybe Alpinus, it's a very static, reliable feature that in a population of Alpinus, you only see the biseriate nature. So sorry for that digression. And Stephanodiscus Organensis, there are 2 valve face remiportula. One is positioned at the near the center of the valve, and then the other remiportula is positioned at the face mantle junction. Stephanodiscus only has a single valve face remiportula near the center of the valve. And then a 4th taxon, which I have not diagnosed, I've not observed it, but would be Stephanodiscus Suzukii, and which is described in Japan, I believe, and just something to take note of when you're working on these medium-sized stephs, again between 10 and 30 microns. That there's many of them that you won't be able to distinguish in on the light microscope, and so if you're calling it Medius, Kutzingii, Organensis, Organensis, you know that there is a level of uncertainty that goes with that name unless you're able to examine the specimens under the SEM. Okay, I could go on about this, but I'll be putting up a Diatom's North America page very soon on this taxon, and if anybody wants to challenge it or help me improve it, please let me know. Okay, so a little bit more distinguished from the Medius complex is Stephanodiscus Organensis, Oregonicus. It was originally described by Hawkinson as Stephanodiscus Oregonica when she transferred it from Cyclotella. However, she amended the name to Oregonicus. And these little stephs, again, you see the spines on every inner fascicle, and the distinguishing feature of Oregonicus is really these larger, more distinguished areolae that composed of the fascicles. They're ending multiseriate. They can be 4 or 5 at the valve margin. But very similar to Transylvanicus, the interfascicle is a lot more distinct than what you might see in Stephanodiscus Medius or Minuculus. One very similar taxon to Stephanodiscus Organensis that I've not had a chance yet to fully explore is Stephanodiscus conspicuoporus. It's a very similar sized diatom with similar fascicle density and distinct interfascicles, and again the fascicles and tri and quadriseriate, pentaseriate nature. So just be careful and knowing when you're looking at something and calling it Organensis or conspicuoporus that these other 2 taxa are available and need to be further diagnosed. If you have a nice population of conspicuoporus, I would love to see it. I've heard it's in the Great Lakes, but I have not encountered many valves of it yet. So here, I guess the next 3 for Stephanodiscus are maybe some groups where there's been a bit more trouble. I know Medius is a problematic group in of its own, but Stephanodiscus Triporis was also described as Stephanodiscus vestibulus. There's a very, I should have shown an SEM of this, but there's a very characteristic vestibule that occurs over the internal opening of, or sorry, externally on the mantle above the folta portula. I honestly think that this Stephanodiscus is pretty distinct and more likely to be confused with Cyclostephanus dubius or Tholiformis, given its high fascicle density. They're concentrically undulate. They're a smaller Stephanodiscus occurring 4 to 11 microns. But the thing that's very characteristic for me is the high stria density that often gives this diatom away. I don't show it in any of my light micrographs, but there is an enlarged spine, a single enlarged spine, which you can sometimes pick up in light microscopy. I was actually just alerted to this from a Diatom Web Academy by Ed Terrio about a month ago, that this was a distinguishing feature. But again, Stephanodiscus Triporis is probably the highest fascicle density Stephanodiscus of the smaller stephs that you might encounter. And I get all right, sorry, I'll go ahead. So another group of maybe a little bit of discretion is the Stephanodiscus hansii group. Hansii is really distinct. It's one of the nearly flat valve-face Stephanodiscus of the smaller ones. Almost all of them are concentrically undulate. Stephanodiscus hansii on the left and formatenuus on the right are considered by many to be the same species, and I guess the formatenuus being an ecological form of Stephanodiscus hansii, the nominate variety. The valves are 9 to 20 microns, and the fascicle difference is one of the things that really jumps out between the 2 forms. Stephanodiscus hansii has a higher fascicle density of 6 to 9 than that of formatenuus, which is 6 to 7. What I often look at in distinguishing these 2 is it's just apparent to me how heavily silicified Stephanodiscus hansii is. The features are very distinct, whereas in hansii formatenuus, the silicification is much lighter. And there is thought to be an ecological explanation for this, that Stephanodiscus hansii formatenuus is maybe a blooming form or a faster growing form of Stephanodiscus when there's higher phosphorus and the population is really growing, and maybe there's a little bit less silica, or the valves are just developing at a greater rate and they're depositing less silica. both forms of hansi have a rosette or an annulus that's a little bit more defined in hansi forma tenuis. They have very prominent spines, unlike in Medius or Minutulus. The spines are very robust and tend to hang on even through processing. Another group of almost thought to be sister taxa, but there is definitely still some discussion out there to be had, is Stephanodiscus Minutulus and Stephanodiscus Parvis. Both are pretty small Stephanodiscus. They are 6 to 12 microns. They have very similar fascicle densities, but there are two key characteristics that really set apart Minutulus and Parvis. In Minutulus, the valves are concentrically undulate, and in Parvis, they are almost flat. And then the valve face, Fultiportula, or the central process, which you can see in the specimen right here, is eccentric. It's set off a bit from the center of the valve, whereas if you observe it in Minutulus, here's an example, and here's an example. The central process is much more centrally located, and there are some specimens of Parvis that I have observed. For instance, fourth from the right here, where you actually have two central processes. I'm not ready to make any form or taxonomic distinctions between the two. I almost always, I struggle to think of a time that I've never seen Minutulus and Parvis co-occurring. There's many times I've seen hansi and, did I say that correctly? I almost always see them co-occurring. There's a lot of times I've seen hansi and hansi forma tenuis existing without the other form, but nearly always do I see Parvis and Minutulus, especially if it's a bloom, the two of them occurring together. Maybe in very low population numbers, if I only see like 5 valves of one per 400 to 600, then I might only see the one form, but generally I always see both forms co-occurring. So I think there's definitely some more interesting work to be done here. First, to just determine whether or not they are the same diatom, and if one's just a form of the other, and then what the mechanisms might be that favor one or the other, or if they're just two species that like the same niche. And so finally, I'll wrap it up here with another small Stephanodiscus, Stephanodiscus penderinus. It's a very, I guess, distinct from all the other Stephanodiscus, especially in the scanning electron microscope. All of the other Stephanodiscus that we've talked about so far, the spines end in a fine point, and Stephanodiscus penderinus ends with a forked spine. I don't know if this is technically enough to move it over to Cyclostephanus, which has spatulate or I believe forked spines, but maybe that's a discussion to have. Stephanodiscus penderinus is often, at 6 to 12 microns. I often see it 6 to 7 microns. I mean, the 12 microns are very rare. It has a higher fascicle density. Like Triporis, the fascicle density can get up to 15 fascicles per 10 microns. And one very distinct characteristic of penderinus is it's often forming chain-like colonies. These chain-like colonies can actually grow in nuisance level growth and have been problematic in the past for municipalities around the Great Lakes. There is a distinct, there's an annulus, an organized group of areolae at the center of the valve forming a little rosette. And then the other thing about penderinus is the valves are often lightly silicified. But really the colony is one of the things that is a telltale sign that penderinus is present, which you see pictured on the far right. And honestly, if you're going really quickly, and I've had to slow myself down sometimes, you might first look at a couple valves that might be stuck together and think you might have some star osiris or something stuck together. And you know, it's when you see the full valve and that the mantle height and then the height, including the girdle bands, just makes for much deeper valves than the star osiris that you might see in girdle view forming chains. If you are working in North America or anywhere and have some populations, here's some Stephanodiscus that I am interested in hunting down. I'm not going to read through the entire list, but what I hoped here, and if I need to clarify anything, I'm happy to, but I was really trying to dive into some of the smaller Stephanodiscus that I've encountered in lakes, and I would love to be able to more discreetly delineate the ecological niches. However, most of the Stephanodiscus are seen in lower abundance unless you have just caught a spring or fall bloom, in which case I think that the presence of that population is really linked to those higher nutrients. And so again, getting back to all the Stephanodiscus being associated with some sort of moving waters or settling out of the phytoplankton after an upwelling of water, but then those nutrients that of phosphorus and silica that are often associated with wind-driven mixing or spring or lake turnover in a larger lake are really, I think it's the buoyancy control and the nutrients that really favor the Stephs. Don't get me wrong, I have seen Stephanodiscus in some larger oligotrophic lakes, but I think they're more, again, indicative of that turnover event than maybe what the ecology of the lake is like all summer. However, I've only been working on diatoms for about 10 years, and I'm sure there are people out there with greater Stephanodiscus experience than me. With that, I'm happy to go back and visit some of these and maybe differentiate and diagnose them better. If you have any questions, feel free to reach out to me outside of the talk as well. Yeah, thank you for your time.
Great. Thank you so much, David. Really appreciate that. And I have a question. Last time in Ed Terrio's talk, he made a really big deal about measuring diameter and total number of spines or fascicles. And how do you resolve that? You talked more about the other method that Sylvie just posted in the chat, where we give that in the diatoms.org. How do you resolve those two approaches?
Yeah, so I think what Ed was particularly getting about is that in diatoms that have really large size range. So first off, I think that fascicle density is sometimes a useful diagnostic feature, but there's a lot of these smaller Stephanodiscus that have overlapping ranges of fascicle density. So it's maybe a higher level diagnostic feature, and maybe it's a key to a taxon like Triporis, which has a distinctly higher density. But the ranges of the size ranges of the taxon that Ed was looking at, you know, they were going from I believe it was 20 to 60 microns in diameter, which would be akin to the Niagara complex. And you know, in there, I think you see a lot of change in the fascicle density. I think in some of these smaller Stephs, the valve range just isn't there, that you get a huge difference in fascicle density between the larger valves and the smaller valves. But I do think by measuring circumferential density and totaling the number of fascicles, you can generate the data to examine that. And that's certainly something that I would like to, I was very intrigued when Ed alluded to that. And I would love to sit down with all of my images and data and see if those relationships hold true in these smaller Stephs. And I think you would have to limited by the size range. You'd really have to examine them, this relationship in the Alpinus and Medius species. I just don't think the 7 to 12 micron minutulus and parvis provide enough of a range to study that relationship. But I will take a look at it at some point, maybe prove myself wrong.
Yeah, it just prompts me to think that we need to be explicit on diatoms.org about what measure is being used. If there are 3 different measures that people are potentially using, and that might apply the wrong one. Mark has a question.
I thought there was few enough people I could do the old hand, raise my hand instead of type it in. It was easier to click that, in fact. David, it looks like we're going to get some additional questions on this, but I wanted to ask you there are two sort of related questions. Number one, is it your sense that when I look at this last slide that you've shown, it sort of hints that there may be some strong biogeographical patterns among the Stephanodiscus. Do you find that the case? And my sort of follow-up question is, when you are analyzing samples, especially for these small steps, do you find that samples are typically just going to be dominated by one taxon and there's a few singletons of other species, or do you find 4 different small steps that are all happily growing together in your samples?
Sure. So maybe all right. So let's talk about biogeography. Within the Medius complex, for example, and within the larger Niagares, I mean, we've shown that Yellowstonensis is through paleo work, endemic to a lake in Yellowstone National Park. I definitely see, I guess, both biogeographical endemisms and then also some cosmopolitan taxa. It's interesting. For instance, penderinus was once thought to be an introduced species, and then some paleo work was done and showed that penderinus was actually around 300 or 400 years in North America before it was introduced or thought to be introduced. And that doesn't preclude it from having been introduced earlier, but it is at least interesting to ponder. But through scanning electron microscopy and the features that are conserved within certain taxa, I've seen European and North American populations analyzed, and there's certainly, Alpinus and Niagara and Medius, minutulus that are cosmopolitan on a much larger scale. But it does appear that the development of these finer ultrastructure features, is a great way to diagnose potential cryptic species or endemisms that we weren't detecting. The difficulty, obviously, is that you have to look at every one of them internally and externally on the scanning electron microscope, and that's unfortunately currently not feasible. As far as how I see Steph's growing, it's very interesting because certain lakes, like the upper and lower Red Lake, for example, there are 2 large, shallow mesotrophic lakes in North Minnesota. I mostly only saw Stephanodiscus Niagara there. And certain Great Lakes, like Lake Erie, you might have a dominance of Stephanodiscus minutulus and parvis, where they are making up over 60-70% of the assemblage. And there's a lot of cases where I might just see one Stephanodiscus. Then there's other instances where you might encounter Stephanodisci. I'm not sure what the plurus of Stephanodiscus is, but multiple Stephanodiscus. There are certainly other instances where in the nearshore environment of Lake Michigan, I have observed 7 different Stephanodiscus taxa co-occurring, but none of them were dominant. It was just, a few specimens from each taxa. So I would think that more work really needs to be done to focus on the dominance of certain species or single species, and compare that to how diverse the representation is from other taxa within the genus. But I guess I've seen a lot of single populations and some mixed populations, to, I guess, answer that briefly.
Okay, so we have some other questions in the chat, David. Layla is following up on endemism, and of course we need to say endemic to what, that term only has meaning if it's attached to a geographic location. But she's asking about endemic. How do you distinguish, or which ones are endemic? And I assume here in North America, is that what you're talking about? Have you just discussed North American species? And of these, which ones are endemic to North America?
That's a very interesting question. I haven't really thought a tremendous amount about that, specifically relating to any one taxon, but I think endemism in diatoms is still a little bit of a problem due to our limited sample size and observations. And even though we've seen a ton of Stephanodiscus Medius and Alpinus globally, we know that the features that really began to diagnose the cryptic or endemic species like Stephanodiscus Organensis are only observed in the scanning electron microscope. And so I think that looking at endemism, especially when the features are restricted to the scanning electron ultrastructure, then it's really difficult to build up a sample size and say like, hey, I saw this here, and we do like to say things are endemic if we've never seen it anywhere else, but I think we should be really cautious about that. So I'm just going to say I don't have enough evidence to really say that a lot of things are truly endemic, because we've only located them once. And there's Stephanodiscus Organensis. There's just a very low number of observations, although one could make the argument that it's endemic to Lake Nipigon, which is just outside of Lake Superior. And the same for Organensis. I'm very hesitant to speak on endemism just based on our limited sample sizes, I guess. So sorry.
Okay, no pinning down David on that one. But something you said leads into Kyle's question about being, using the SEM, and that if these differences are based on SEM features, how do you work with that in your analysis?
Right. And so this is where you have to realize your own limitations, I think. And so if I'm calling something Stephanodiscus Medius, there's probably 3 or 4 other names that I should do my diligence and list that it might be. And unfortunately, that's the nature of this beast, and we certainly encounter it with other species complexes and groups within diatoms. But just as we're trying to document what we can with the light micrograph and build voucher floras and be careful, I think we have to recognize where some of the limitations of the light microscope fall, and then how do we diligently report that. And with confidence you could say it's Stephanodiscus Medius, Agassizensis, Kutzingii, and Organensis, and that's the best you can do until you get it on the SEM. So I guess making a footnote, adding the caveat, and putting that out there is really the best you can do at the microscope. Maybe in the future, if people figure out what works and doesn't work, DNA examination may be a more suitable way than or more economical way than using the scanning electron microscope. But there's a lot of work to be done and bridging both of those fields together. So I guess, Kyle, what I would say is recognize the limitations, and I guess don't be forthcoming about them. And right, it's the thing in science, like the more we know, the more we know we don't know. And so just being a diligent scientist or analyst and being forthcoming with that taxonomic shortcoming, I think, is the best.
So following up on that, Mark asks, perhaps this is coming from too, given that we all, or not all of us, but some of us are working in terms of using diatoms to indicate some type of condition. Can you say a few words on the indicator values of any particular staph species? And just even how well do we understand any one of them's odd ecology?
Yeah, I think we have a really great fundamental understanding of the ecology for a lot of these Stephanodiscus. I think there's, as I've kind of alluded to, some things you have to be careful with. I'll start with the easy. Blooms of Stephanodiscus minutulus, parvis, hansi, hansi forma tenuis, penderinus, often indicate very eutrophic, high total phosphorus conditions, high silica, it's a little more tricky with Medius and Alpinus and Niagari, as I would label them a little bit more mesotrophic diatoms. But again, it's not that these diatoms can't be observed in oligotrophic lakes, and then you have to start thinking about that ecosystem outside of just the time you sampled it, right? And I guess we'll have to step away from rivers and just think about lakes, and that lakes have lots of different internal processes that occur seasonally or based upon weather. And I have a little visitor, if you can see them right there. I don't know. I'm still sharing my screen. You can't see them, but you can have a lake turnover, and nutrients can be brought up as the waters are stirred around. And if you were there measuring the lake and observing the lake during the fall turnover, you might record higher nutrients and a different diatom community. However, most of the summer the lake might be stratified and have lower nutrients, and you end up having some of these Stephanodiscus that have figured out how to stay buoyant or have lucked out and stayed buoyant. You might observe them in your sample. So it makes it really difficult then to tease out specifically what is the indicator value versus what is the ecology of that Stephanodiscus. We want indicator values because they're a tool, but as we look, diatoms can grow and bloom, and maybe once they've established themselves, the conditions can change, and to some degree, the diatoms might still be able to persist. They might not be a blooming population anymore. So I think there's a lot to look at the odd ecology of all of these, and understanding perhaps their growth and blooming dynamics might be more pertinent to their indicator value.
Okay. If anybody else has any questions, you can raise your hand or just jump in and say something, or put it in the chat. I wanted to also invite all of you, any of you, to participate in the Diatom Web Academy. It's a great way to meet people, to be a part of the community, to take part in inviting speakers or making contact with them. And we would love to have you on our team. So think about it. If you're coming to the Diatom Web Academy, think about just joining in to host. Yeah, Layla. Go ahead.
Yes, hello, David. Thank you. I wanted just to ask you if you compared your Stephanodiscus with those in the valley of the Afar lakes, where we have always alternance between Stephanodiscus and Olacoseira, depending of the season. Have you noticed in your lakes some other species with your Stephanodiscus, and have you looked at some similarity in between? Thank you.
Yeah, no, thank you. That's a really great question. I guess part of my problem is I've looked at everything from really small prairie potholes to Lake Superior and everything in between, and I have certainly seen some associations, and it all depends on the system that you're looking at. You know, in a larger stratified lake, you know, like Lake Superior or one of the Great Lakes, it doesn't even have to be like that big, you're going to see, you know, some more usual characters of the phytoplankton, the Asterianellas, the Lindavias and Cyclatellas, that might be associated with the assemblages of the Epilimnion in these systems. However, you also see Stephanodiscus in shallow lakes, and there the Stephanodiscus are associated with small araphid chain forming Pseudostarosiras, Starosiras, and Fragilarias. To say that Stephanodiscus belong with any other one taxa, I can't make that distinct association. Now, of course, you see, so Olacoseira is another great centric genus, one of my favorites. You know, they're heavily silicified diatoms, and so they're reliant on some of the same physical limnological features that Stephanodiscus is reliant on to survive. They need that mixing of waters, they need that upwelling, and you see these fall and spring blooms or constant blooms in shallow mixed lakes. And interestingly, I'm still trying to tease it apart, but we took some sediment cores, and I almost tried to present some of that work in this talk, but we took some sediment cores along the Poplar River. Sorry, I'm going to get this wrong. Sorry, in southern Minnesota, we took some sediment cores, and it was really interesting because you would see Olacoseira and Stephanodiscus communities responding in the same ways throughout the sediment core, which would often indicate to us that there were periods when the lakes were more prone to mixing or less prone to mixing, and in these regions that was thought to be driven by the presence or absence of aquatic vegetation. But then there were some instances where the Stephanodiscus would be very prominent and the Olacoseiras would be absent, or the opposite. So you know, while they do have some very similar mechanistic life strategies, where they're reliant upon moving waters within a lake or a river, there are still some ecological factors that maybe aren't accounted for. Maybe there's something Mark could jump in and answer a little bit more, but it's things for David to learn on his quest of getting to know diatoms over his life. So I will think about that and try to get back to you more. But it makes sense seeing the Olacoseiras and the Stephanodiscus blooming together, for sure. Oh, and I see someone made a post. Oh, Mark made a post about the solstice party. He threw the link in the chat. So don't forget, on December 21st at 6 p.m. Eastern time, Eastern US time, there's a diatom solstice party.
Great. Well, thank you, David, for sharing with us all the information on Stephanodiscus. Really appreciate that. And thank you everyone for joining. Best wishes for a warm and safe holiday and a happy new year. And we will see you in January for the next, the 2023 season of the Diatom Web Academy. And again, we welcome anyone who would like to join in as part of the hosting. Just go ahead and get in contact with one of us. Okay, take care, everyone.
Thanks, Sarah.
Thanks, David.